All right, this is the section 5.2 exponential function video for the day that we're missing on the week of Thanksgiving. So this is to get everybody caught up so that when we come back from Thanksgiving, we'll be back on track to finish strong for the end of the semester. We need to talk about what we're talking about in this situation. What are these functions and what are we going to be doing with them? So before, just to give you some reference points, we have dealt with things like f of x equals x squared, f of x equals x cubed. Notice that the variable was a base in both of these. Now we're going to be looking at things like f of x equals 2 to the x, where the variable is an exponent. So an exponential function is one where the variation or the change, the variable, is happening in the exponent. So for us, we don't talk about base 1 or base 0. It's going to be something other than that, so like a fraction or something bigger than 1. And then x is going to be an integer of some kind usually, or it can even be a real number if you want. It can be any number in the real number line. So the domain of an exponential function is going to be negative infinity to infinity. We can plug in any real number on the number line for that exponent. The range we're going to find out is, if you look at this picture, if you plug something in, even if it's a negative exponent, it's just going to make it flip the fraction upside down. So it's not actually going to make the number negative, it just flips the fraction. So notice we never cross below this 0. So our range is 0 to positive infinity. Now, if our base is bigger than 1, so things like 2 to the x, 3 to the x, 4 to the x, then we see that our graph is going to be growing. It's called a growth function. If your base is between 0 and 1, so like 1/2 to the x, 1/3 to the x, 3/4 to the x, usually those are in parentheses, then you're going to have what's called a decay function, where you get smaller on the y-axis from left to right. The growth functions are usually dealing with financial situations like money sitting in an account over time, earning interest. Decay, there's a lot of different things, but like medicine leaving your body or your bloodstream. Radioactive decay, if something radioactive goes off in an area, it decays over time quickly at first, but then there's still remnants for a long time. And just like money, grows slow at first, but then really starts to shoot off as you let the compound interest work. So this is the two cases. We've already talked about which one's the growth and which one's the decay function. If 0 is to the 0 power, so if a is 0, then it's undefined. That doesn't make any sense for us. And if a is 1, that's why we don't talk about this case, you get a horizontal line, because 1 to any power is always 1, so it's just a flat line. So here's our formal definition. The exponential function f of x is given by a to the x, where a is between 0 and 1, or a is greater than 1, so the decay or growth. And that function is 1 to 1. It passes the vertical line test, so it is a function, and it also passes the horizontal line test. Thus, eventually it's going to have an inverse. So that's something important to know. So when using this theorem as a reason for a step in the solution to an example, we're going to be solving some exponential equations. And since they're 1 to 1, we can use this nice little property. This property only exists because of the 1 to 1-ness. So it says if you have the same base on each side, so 3 to the 4th and maybe 3 to the x. The only way this statement could be true is if the two exponents are also equal. So same base, and notice it's one base on each side, we set the powers equal. So let's look at this first example. Same base on each side, so we set the powers equal. So we're going to be solving 7 minus x equals 2x plus 1. We'll add x over, subtract the 1 over, divide by 3, and x equals 2. Notice that in B part, it's not the same base, but 9 can be rewritten as 3 to a power. So as long as you can rewrite it as that base to another power, you can get this to work. You cannot divide anything out or make this one bigger. You can only rewrite a number as something to a power. And then when we do that, we have to use the laws of exponents. So this is now 2 times x squared because it's power. So that's 2x squared. So now that we have same base on each side, we're going to set 2x squared equal to 3x plus 2. Now that's a quadratic, so we'll want to solve over everything to one side and see if we can factor by grouping. So 2 times negative 2 is negative 4, which the only factors are 1 and 4 and 2 and 2. To make negative 3, it would have to be a positive 1 and a negative 4. So 2x squared minus 4x plus 1x minus 2 equals 0. We can pull a 2x out of the first pair. That leaves us with x minus 2. Nothing to pull out, so we have to pull out a 1. That also leaves us with x minus 2. So x minus 2 times 2x plus 1. Looks like we're getting two solutions, positive 2 and negative 1/2. Now, because exponentials have a domain of all real numbers, we don't need to check these solutions. So that's why I'm not doing a check here. So then this one's a little funnier because it does have a 2, but it's in the wrong location. So if you have something in the wrong location, you pull it to the top and use the negative exponent rule. So since this is 2 to the first, if we pull it up, it'll become 2 to the negative 1. Keep that power that was already on the outside. This is 2 to the first. This is power. So if you have two powers, you multiply, and that would have to be distributed. So that's going to be negative 6 plus x, 2 to the first. Now that we have same base on each side, we can set the powers equal. Solve by adding over the 6. So x equals 7. Okay, this one, 9 and 27 are not the same base, and you cannot write 27 as 9 anything, like easy. So 9 squared is 81, so that's already too big. But we can make both of them smaller, so keep your powers on the outside, by using the same base 3. This is 3 cubed, this one is 3 squared. So this would be 3x minus 3. And this will be 4x minus 6. So if we set those equal, now that they have the same base on each side, subtract the 3, that would just be x, add the 6, which would be 3. Okay, and then this last one's the doozy. This is the one that is the most difficult out of all of them. So it looks like we have a base 3 thing going on because 9 can be written as base 3. 1/3 is on the wrong location. So a negative exponent will have to come in play. 27 can be written as a 3, and this one's already a 3. So let's just rewrite everything first. So this is 3 squared to the 2x times 3 to the negative 1 to the x plus 2 equals 3 to the third times 3x to the negative 2. Be careful here. A lot of people want to write this as x minus 2, but this is power, so it's going to be multiply. So this would be 3 to the negative 2x, 3 to the third, distribute here, 3 to the negative x minus 2, multiply, 3 to the 4x. Okay, the problem is this cannot all be set equal to each other yet. You're supposed to only have one base on each side, so we're going to have to use another rule of exponents. If you have the same base and you're multiplying the x's together, we add the powers. So remember that was a rule. So we're going to be adding our powers here. So 3 to the 4x minus 1 would be 3x minus 2, because this is not a like term with that. And this would be 3 to the 3 minus 2x, since those are not two like terms. Now we set the tops or the exponents equal. Let's add over the 2x, add over the 2, and x equals positive 1. So all that work and x was just positive 1. So that's how we use this to solve equations that can have the same base on each side. The other thing we're going to do in this section, there's three things. We're going to learn how to graph some exponential functions. And all of the graphing in this unit is pretty much done by a table of values. You can use transformations like section 3.5. I would not usually recommend it, especially if you weren't strong on that already to begin with. And a table goes pretty quick. So if we look at this, this would be, I usually go -2 to 2. Unless there's a reason not to, and I'll show you when there's a reason not to do that later. 3 to the -2 would be 1 over 3 squared, which is 1/9. 3 to the -1 is 1 over 3 to the first, which is 1/3. 3 to the 0, anything to the 0 is 1. 3 to the first is 3. 3 squared is 9. So we plot what we have. So -2, 1/9. -1, 1/3. 0, 1. 1, 3. And 2, 9. Notice this has a natural horizontal asymptote at y equals 0. We always graph that in. And that's because, remember, the domain of this function was all real numbers, but the range was greater than 0. So let's look at this next one. Now, this one's a little bit different because this one has a negative in front. So remember what that does is that flips you upside down over the x-axis. So we want to see if that actually happens here. -1, 0, 1, 2. So -3 to the -2. This negative does not affect this negative out front. This is negative now 1 over 3 squared. So that's -1/9. -3 to the -1 would be -1 over 3. -3 to the 0 would be negative, and then 3 to the 0 is 1. -3 to the first is just going to be -3. -3 squared is -9 because you're not squaring the negative. Remember, if it's in front, it's after you've been squared. So this one is plotting this just pretty much upside down from the original, which is what the transformation would have been. Sorry, my nose is really messed up from allergies. And you still have your horizontal asymptote at y equals 0. Unless we do a vertical shift, that's going to stay there at y equals 0. And speaking of shifting, remember when we learned how to do transformations, we did learn how to do both vertical and horizontal shifts. Notice this is -2 not included in the 3x. It's happening after it. That's a vertical shift. So this should shift the whole graph originally down 2, just if we were talking about transformations. So if we do it on our table, this would be -2, -1, 0, 1, 2. This is 3 to the -2 minus 2. That is 1/9 minus 2. So let's see, that's going to come out to some kind of decimal. So 1 divided by 9 minus 2. That's -1.89. Okay, 3 to the -1 minus 2 is 1/3 minus 2. And you could probably do this in your head, but I'm going to use my calculator. So we're just trying to get in the right area, so that's -1.67. 3 to the 0 is 1. 1 minus 2 is -1. 3 to the first is 3. Minus 2 would just be 1. 3 squared is 9. Minus 2 is 7. So this is -2, -1.89. -1, -1.67. 0, -1. 1, 1. And 2, 7. So notice the same graph as before, but the whole thing has been shifted down 2, which means your horizontal asymptote has also been shifted with that vertical shift. So it's at -2, which is the constant that was at the end there. Okay, if you have a plus or minus 2 inside the exponent, that means you're doing a horizontal shift. Remember, horizontal shifts happen to something before you do anything else. Ooh. Hang on just a second, something weird's happening with the screen. Okay, so I know that a +2 inside here should be doing the opposite. It should be going left 2. So I already kind of know that by transformations, but the problem with doing a table on this one is that you never want to do -2 to 2 if something complicated is happening in your exponent. This is shifting your table. You want to shift this till whatever makes that equal to 0. So that's x equals -2. That's going to be the middle of your table, not 0 anymore. That's so that we get a 3 to the 0, which is what we want. And then we do 2 things smaller and 2 things bigger. So this is the only time your table is really not -2 to 2. So -4 plus 2, that's going to be 3 to the -2, which is our 1 over 9. So this gives us the y value we know. 3 to the -3 plus 2 is 3 to the -1, which is 1/3. And this all works out the way that we want. So you can check it. 3 to the -2 plus 2 is 3 to the 0, which is 1. Sorry, I wrote 0 there. 3 to the -1 plus 2 is 3 to the first. 3 to the 0 plus 2 is 3 squared. So if we plot this, this is -4, 1/9, -3, 1/3, -2 at 1, -1 is at 3, and 0 at 9. So it has shifted my graph 2 to the left. And then this is still a horizontal asymptote of y equals 0. Now, the only time the asymptote changes, remember, is with a vertical shift in these kind for the exponentials. And then we have 2 more of these. This is 3 to the -x. So you can still do your -2 to 2 since there's no plus or minus anything there. Because if you solve that, that's still going to be 0. But what you're going to see is this graph's going to go opposite of what we think. This is 3 to the -2. So that's going to be 3 squared, which is 9. 3 to the -1, which is 3 to the first. 3 to the -0 is just going to be 3 to the 0, which is 1. 3 to the -1 now, though, is going to be 1/3, and this one will be the 1/9. So -2, +9, -1, +3, 0, 1, 1, 1/3, 2, 1/9. So now just notice this is the first time the function has been a decay function. And we said decay functions have bases that are between 0 and 1. This is a base 3. That's because you could have rewritten this as 1/3 to the x. Because that's a -x, you can flip it upside down and make it a +x, which is the very next graph. So I'm not going to graph this one again because this is the same as 3 to the -x. So it's the exact same graph. And you could do that by doing -2 to 2 if you wanted to, but it's the same graph we just did. So radioactive decay and compound interest are 2 applications we're going to use a lot for this unit. Certain physical quantities will decrease exponentially. In such cases, if a is the base of the exponential function, then 0 to 1 is the base. So we know it's a decaying function if it is between 0 to 1 and the exponent is positive x. One of the most, or you can sometimes just tell this if the exponent's negative. Sometimes that will also tell you, oh, this is a decay function. One of the most common examples of the exponential decrease in the decay of radioactive substances or isotopes. The half-life of an isotope is the time it takes for 1/2 of the original amount to decay. So if you had 100 milligrams of something radioactive, we want to know how long did it take to get it to 50 milligrams. And that's the principal characteristic used to distinguish one radioactive substance from another, is how long does it take to decay half of the way. So compound interest is the other application, and it's a good explanation of what growth looks like. So principal is the money that you put in. Then we know that we're not going to go through simple interest. That's not on our test. So this is the formula we need for compound interest. Let me give it down here. So this is what we're going to be using most of the time. So A equals P, which is our principal, parentheses 1 plus our rate as a decimal, like 8% would be 0.08. How many times they compounded a year means how many times do they apply the interest in a single calendar year. So if they do it quarterly, that would be like 4. If they do it monthly, that would be 12. Daily could be 365 or 360, depends on if they use Banker's Rule. Banker's Rule eliminates 5 days, so it calls it 360. Typically daily, though, would be 365. I think our book does go with Banker's Rule, though, so you probably would use 360. So it should say somewhere in the directions what it's telling you to use. And then T is the number of years you're going to let the money sit or invest. So that's the formula. It is provided on the test. You do not have to memorize it, but you do not have to plug in and solve it. So let's look at some examples. Sorry, my nose is really bad tonight. Drug dosage. So a drug is eliminated from your body through urine. Suppose that an initial dose of 10 milligrams, that's how much they're going to inject into you. The amount A of T in the body after T hours is given by this formula. So that's our formula. I already know this is a decay function because 0.8 is between 0 and 1. So we know it's decreasing out of our body, which makes sense. If you've been given a drug, it should start to break down. The first part says estimate the amount of drug in the body 8 hours after the initial dose. So that's just plugging in 8. So A of 8 is 10 times 0.8 to the 8th. So 0.8, not times, 0.8 to the 8th, and then times by 10. Looks like 1.68. And this is in milligrams. Now, what percentage of the drug would still be in the body, that's still in the body is eliminated each hour? To figure that out, you'd have to look at, okay, so what's a couple different hours and how does the percent change from hour to hour? So let's do, say, A to the 0, A to the 1, A to the 2, just so we can get a little general idea of what's going on. Now, 0 is when you just receive the drug. So this is to the 1 right here, because 8.8 to the 0 is 1 times 10. So that's 10 milligrams. No drug has left your body. And this would be 0.8 times 10, so that's going to be 8. That does not mean you lose 2 milligrams every hour. It's just we're going to look at the percentage. And this is 0.8 to the second, so we need to work that one out. 0.8 squared times 10, so that's going to be 6.4. So there's a formula that will allow you to find a percent of change. It's called old minus new, or sorry, new minus old. We want it to be positive on top. All divided by old. So this is called percent change. So this would be, the new is the more recent hour. So this tells you if it's decreasing or increasing, if it's positive or negative here. So that's 8 minus the old, which was 10, divided by the old. So that's negative 2 over 10, or negative 0.2. That means it is decreasing 20% per hour. Because 0.2 as a decimal turned back into a percent would be 20, because you'd multiply by 100. So I could have figured this out a different way, which would have been a little bit quicker. If this is 0.8, that's how much drug is still in your body. So the opposite of that is how much is leaving your body each hour. So 0.2, because it has to add up to 100%. So just something interesting to see there. Okay, so here's another example. Actually, we're going to X this one out. This one is no longer one that we make you do. We don't make you graph anything for that. So let's look at example 5. If $1,000 is invested at a rate of 7% compounded monthly, find the value after 6 months, 1 year, 5 years, and 20 years. Okay, so we're doing that compound interest formula. And we're going to do one for 6 months, which 6 months is not years. Since our formula is in years, we'd have to make that half a year. And then we have 1 year, 5 years, and 20 years. So we're going to have a formula for each of these. So A equals $1,000, parentheses 1 plus 0.07, compounded how many times per year? 12 for monthly. And that's 12 again, because it ends on the outside, times the number of years. So this one's a half. So I always figure out what this is. This is 6. That's easier to plug into my calculator. So 0.07 divided by 12 plus 1 raised to, notice I'm not clearing anything as I go, 6 times 1,000. That is 1,035.51. Okay, let's do 1 year. Still the same rate, same number of compoundings per year, but now it's 1 year. So it's going to be the 12th power. So 0.07 divided by 12 plus 1 raised to the 12th power times 1,000. That's 1,072.29. Let's do 5 years. Now this is the power of compound interest. Now this is a exponent of 60. So it's been sitting there for a while. So let's see, this would be 0.07 divided by 12 plus 1 raised to the 60th power times the 1,000 initial deposit, 1,417.63. Okay, and then 20 years, which is letting it sit for a lot longer. So this is really an easy question usually to just sit and plug and chug. This is 240 for the exponent. So 0.07 divided by 12 plus 1 raised to the 240th power times the 1,000. 4,038.74. So notice this really grew that last 15 years. It quadrupled almost. So it did quadruple from the original amount. So this is kind of interesting to see how the money grows the longer you let it sit. That's why we tell you invest early and let it sit for a long time. And, you know, just that's why retirement works that way, because of compound interest. So the last example has us solving this a different way. It says if a savings fund pays interest at 6% compounded semi-annually, that's one we didn't talk about. That's 2 times a year. Semi usually means twice a, annual means 1 year. So how much money should we invest now to get 5,000 after 1 year? So 5,000 is A. So A equals P parentheses 1 plus R over N to the NT. Rate is 0.06. Time is 1 year. I think we have everything but P. So this is 5,000 equals P parentheses 1 plus 0.06 over 2, all to the 2 times 1. So my exponent's 2. I usually resolve this for P. So this is 5,000 divided by parentheses 1 plus 0.06 over 2 to the 2. Now, when solving for P, specifically P, always round up. So if they tell you to round up to the nearest dollar, round up to the nearest dollar, whether or not the 0.4 or 0.6 or whatever follows it. If it's nearest cent, round up to the nearest cent, no matter if it rounds up naturally or not. The reason for that is you are trying to figure out what to start with to reach a goal. If you round down, you're going to fall short of the goal. So let's type this in and see what we get. So this is 5,000 divided by parentheses 1 plus 0.06 divided by the 2 times a year raised to the 2 power for 2 times a year for 1 year. and that is 4,712.98. I would have rounded up no matter what. In fact, we can round to the nearest whole number here. So 4,713 because I didn't specify. Now, that means you had to pretty much have all the money because you're only letting it sit for 1 year, so you're not going to make a ton in interest, but they're saying you make a little less than 300 in interest in this situation. So that's it. So hopefully these notes will be good and easy to follow. There'll be a worksheet attached, remember, for you guys to try a couple problems on your own to turn in when we come back from Thanksgiving break. So have a good time with, friends and family, and I'll see you guys after break.